All right. Well, hello, everybody. Thank you for coming. It's my pleasure to introduce Raghav Malik. We actually met maybe 3 years ago now, something like that, at a PLT event. And we've been sort of Twitter mutual followers ever since. And I've been admiring his work from afar. And back then we talked about oblivious computation and PL. So I'm glad to see that he sort of stayed in that lane. Today he's going to be talking to us about a compiler for vectorizing encrypted arithmetic circuits. Take it away, Raghav.
Right. Hi, thank you for the introduction. As I mentioned, my name is Raghav Malik. I'm from Purdue, and this is actually pretty similar to a talk that I gave a few weeks ago at ASPLOS about my paper Coyote, a compiler for vectorizing encrypted arithmetic circuits. So this is work that I did with my collaborator Kabir Shait and my advisor Milam Kulkarni. I'd like to start the talk by giving sort of a brief overview of fully homomorphic encryption. So this refers to sort of any encryption scheme that has this nice like homomorphic property over ciphertexts, which means that let's say I've got two parties, Alice and Bob. Alice can take two numbers, X and Y, encrypt them and send the ciphertext over to Bob. And then Bob can directly add the ciphertext to get an encryption of X plus Y and send that back to Alice, who can decrypt it to get her final result. And crucially here, Bob knows that he's adding two numbers, but he only sees the ciphertext, so he doesn't actually know what X and Y are. Like he doesn't know the actual values. So that's FHE. For a bit more background, in most implementations of FHE, ciphertexts are represented as these very high degree polynomials. And this has a couple of consequences. First of all, it means that homomorphic operations over ciphertexts are incredibly slow. And in particular, multiplication is a lot slower than addition because just like multiplying really large polynomials is like a very expensive process. But the sort of upshot to all of this is that this polynomial encoding gives us some kind of built-in vectorization, which means I can take a bunch of individual numbers, like individual plain texts, and pack them into a vector and encrypt that whole vector into a single polynomial ciphertext. And then when I do computations over like ciphertext vectors that are packed this way, like addition and multiplication corresponds to adding and multiplying the doing it like element wise. And so we can try to like recover some of this like slow performance by vectorizing computation. And then a sort of crucial quirk of computation in FHE is that control flow can't depend on any kind of secret data. So in particular, that means that all loops can be fully unrolled because I can't have any kind of like ciphertext bounds on my loops, so that I have to know at plain text time how many iterations I'm going to run. I have to be able to fully inline all function calls, and like any conditionals I have to have branches that are fully plain text. And so I can always like just choose one branch at compile time. So I don't have to worry about any of these like control flow structures in my final program. And so in particular, that means that it suffices to sort of think of all of these computations as just happening over like arithmetic circuits, which don't have any of these control flow. Okay, so for a bit more like specific details on the paper, the high level idea is, as I mentioned, FHE is very slow, but we can try to make up for this by vectorizing. And in particular, our contributions are an FHE-aware algorithm for vectorizing arithmetic circuits like the ones I described, and a DSL called Coyote, and a compiler which implements this algorithm. Now, I called our vectorization algorithm FHE-aware, so I'd like to talk about why exactly that's necessary. So if we look back at like classical, like old school vectorization, it sort of like traditionally happens over loops. So here I've got like a data dense loop that iterates from 0 to 16 and adds the elements of one array to the elements of another array. And like the classic thing I can do here is take this loop and unroll it 4 times. And so now I've got 4 copies of the same statement, and I'm still iterating from 0 to 16, but I'm going up by 4 each time. And now, because I have 4 copies of the same statement, it's very easy to just pack these into a single vector instruction. And, you know, all the memory accesses are aligned and all of the sort of everything is isomorphic. And so this is just very easy to do. But of course, in the FHE world, we don't necessarily have access to data dense loops like this. And we'd also like to be able to do something a little bit more general. Unfortunately, there is a style of vectorization that kind of gives us some of this called SLP, or superword level parallelism. I've got a reference to the paper that introduced this down at the bottom. But the basic idea behind SLP is you can have just any sort of sequence of instructions. It doesn't have to be packed into a loop. And SLP will try to find sets of instructions that don't depend on each other and also are isomorphic, and it'll try to pack those together. So here we can see we've got like 3 loads, 3 constant assignments, and 3 adds, and none of those like depend on nothing in like a set of instructions depends on something else in the same set. And so it can like reorder these this way and pack them into vectors this way. And this seems really cool. And actually, it seems like we could just directly use this, but there's a sort of subtle problem in the FHE computational model that makes this maybe not a great idea. So before I can explain what that problem is, let's actually look at what vectorization looks like in FHE. So the vector operations we have are, we've got a plain text, ciphertext, addition, and multiplication. So when one of the operands is a plain text, this is actually very cheap. We've got a ciphertext addition, which again happens element-wise in the vectors. This is also relatively cheap because it's just adding 2 polynomials. We've got a ciphertext multiply, which is, again, element-wise, but this is very expensive because it's multiplying 2 polynomials and like doing some extra work on top of that. And then finally, we've got this like cyclic permutation or rotation operation, which takes everything in the vector lanes and sort of like shifts everything over by the same amount. And crucially, this is the only, this is also very expensive, and this is the only way that we have of moving data between different vector lanes. So in particular, there's no like gather scatter instructions or pack unpack instructions because we can't like index into a ciphertext. And so this means that sort of worrying about like these data movement operations becomes kind of a pretty big hassle. And for an explicit example of where this shows up, let's take a look at this this arithmetic circuit that I have. Now, a priori, this seems like it would be super easy to vectorize, right? I've got a bunch of operations, they all line up, there's, everything just looks very clean. So let's try to vectorize it. At the first level, I've got 4 adds, so I can take all of my left and all of my right operands and pack them into one instruction. At the second level, I've got 2 multiplies, so I can take the left operands for that and the right operands for that. And then at the top level, I've just got 1 addition, so I pretty much just have to do that in scalar. Now, this vector schedule that I have here on the right has a couple of issues with it. Mainly, you can see R1 and R3, which are like I've sort of highlighted in pink here, get produced on lanes 2 and 4 of their vector, but they get used on lanes 1 and 3. And so to make that line up, and sort of similarly, R5 gets produced on lane 3, but it gets used on lane 1. And so to make everything line up, we have to insert these 2 rotates, right? So I take the results of the first vector and rotate everything back by 1, and that corresponds to those 2 edges that I've highlighted in blue. And then for this other one, I have to rotate everything back by 2, and that corresponds to that other edge that I've highlighted. And so to actually make the schedule work out, I have to insert 2 rotates. And so what's essentially ended up happening is by vectorizing, we saved 3 adds and 1 multiply, like compared to the scalar schedule, but we incurred a cost of 2 additional rotates. And if you remember, the multiplies and the rotates are the expensive ones and the adds are the cheap ones. And so this turns out to actually not be worth it. And in fact, like by vectorizing, we've actually made everything a lot slower because like the overhead of rotating is just so high. So this is really bad. And the question is, can we do better? Like, is there a schedule that for this particular problem, let's say, that doesn't suffer from this issue? And the answer is yes. And so I've just written out the schedule here on the right. And you can see it corresponds to taking these 2 edges that we rotated along in the first one and just getting rid of them and like putting that add and that multiply together into the same node. And this kind of changes like the level that everything exists at. Just for a bit of terminology for the rest of this talk, I'm going to call this new like contracted circuit a quotient circuit. And so now you can see at the first level, I've only got 2 adds. At the second level, I've got the add and the multiply. So I do the add and I do the multiply. And then the third level, I've got that add. And so I've sort of given up a bit of this vectorization by doing this contraction. But now you can see the only rotate that's necessary is for R5. And so if I insert that rotate, that like the schedule lines up perfectly. And now we've saved 2 adds and 1 multiply at the cost of 1 rotate. So we didn't save as many additions. Like we had to do an extra add, but we we got rid of one of those rotates, and that turns out to actually be worth it. So I've sort of shown you like for this specific example how we can do better. And the trick was sort of like contracting this edge away, and it sort of like, I don't know, like introduces like an extra dependence or like forces us to give up a certain amount of vectorization to avoid like over vectorizing. And this turns out to be like a very good framework to think about this whole trade-off spectrum, right? Because on one end of the spectrum, we've got the like very aggressive SLP approach, and we can think of that as like quotienting by a trivial circuit or not collapsing any edges, and that's what we did at first. And that's vectorizing everything possible and like not worrying about data movement at all. On the other end of the spectrum, we could care a lot about data movement and avoid that at all costs. And that's the sort of like very conservative scalar approach, where we quotient the circuit out by its connected components and just like collapse every edge. And so that's like doing no vectorization at all. And of course, what we want is like maybe something in this trade-off space, somewhere in between, where maybe we quotient by something, but not everything. And this is essentially the approach that Coyote takes of like trying to find a good quotient between these two extremes. So the specific way we frame this is as this like huge search problem over this huge graph of quotients. So you can see this is a graph where every node represents a potential circuit, and the edges correspond to like contracting specific edges. So you can see this like node on the left here is like our original circuit, and then the two edges going to the right are like contracting different things there, and sort of every contraction results in a different circuit, and we can kind of like search over this graph. And so we start at the root and perform a search, and at every step like sort of try to see how good the schedule would be at that step, and try to find a path that leads to the optimal schedule. So it's just a giant graph search. But of course, to be able to do this, I have to have some kind of cost model, or I need to know like how good a quotient is. And this turns out to be a little bit complicated, because there's this thing that I kind of glossed over when I was showing you the schedules earlier, which is like lane mapping, right? So every scalar instruction has to be mapped to a particular vector lane. Like I chose to put the things in, like I chose to put R0, R1, R2, and R3 in that particular order. And if I had picked a different order, it would have given me like worse, it would have like maybe incurred more data movement that wasn't strictly necessary. And so you have to sort of pick a particular lane mapping when you generate a schedule, and different choices of lane mapping give you different like rotation policies and sort of a better or worse schedule based on that. And so for every step that we take through the graph, we get a different circuit, but then we have to optimize the lane mapping for that particular circuit to figure out what the best possible schedule is for that set of contracted edges. And so this leads to like a sort of two-layer search, where on the inner layer, so for a particular node in that graph, we do some kind of simulated annealing to figure out what the optimal lane mappings are, and then do a beam search over the graph in the outer layer. So this is like you take a step through the graph, you do simulated annealing to get your cost, and then you take another step through the graph, do another round of simulated annealing to get a new cost, and then kind of like do a beam search over all of these. So this is very like expensive two-level search procedure, but it turns out to like converge to pretty nice schedules for most of our like reasonable benchmarks and stuff. Okay, so that's kind of the search procedure that Coyote uses. Let me talk a little bit about the DSL. So it's embedded in Python, which is nice because Python sort of automatically like unrolls all the loops and inlines all the functions for us, and it kind of like forces you to not put like a ciphertext bound into your loop. And it stages away any plaintext, like you can do any other plaintext computation, and it just like fully gets staged away and just produces an arithmetic circuit at the end. And then the DSL gives you this option to replicate or unreplicate your inputs, which ends up being kind of important. So for example, if you have a circuit where like I've got this sort of abstract circuit on the left where the circle input is being used twice in the square input, I've got two options here. I can take the circle and rotate it 2 different times for the different places that it gets used, or I can replicate it and just pass 2 copies of that input in. This is a trade-off that we sort of leave up to the programmer, but replicating generally means you have to do fewer rotations because you've got like more copies, like one thing doesn't have to go to 2 different places. But it does come at the cost of like maybe doing some computation twice, or like using up more vector lanes or something like that. And then finally, at the level of the DSL, you can specify that some inputs need to be packed into ciphertext vectors. So if you're doing like a matrix multiply, you might say that like all of the n squared entries of the matrix should be packed together, and that'll sort of like inform the schedules that Coyote produces. And then Coyote takes the circuit along with all of these like constraints, like the replication constraints and the packing constraints, and it does the vectorization procedure that I described earlier, and it generates C++, which just links against some like Microsoft Seal's FHE library. Here's a couple like examples of what the DSL looks like. So this is like the unreplicated version of a matrix multiply. So you can see I have like a dot product, which is just a plain Python function that like gets the like loop gets unrolled, the like zip function gets inlined and all of that stuff. And then I've got my actual matrix multiply down below, which is annotated with this Coyote defined circuit annotation, and that tells it to sort of like run it symbolically to actually produce a circuit. And then I've told it that A and B are inputs that should be unreplicated. And so you can see the like IR, the vector IR that it generates down below. And the thing to pay attention to here is all of the multiplies get packed into one multiplication operation, which is that V2, but there's two rotates. So there's S0 and S1 are the two rotates that this incurs. On the other hand, if I allow it to replicate all my inputs, so you'll notice none of the A's get replicated, but like B gets replicated twice. So like here, I've just got B0 and B1 passed into T1. But here I've got B1 passed in twice and B0 passed in twice into T1. And so my vector sort of has more entries in it, but you might notice all of the multiplications still happen in one step, but there's only one rotation with S0. So this is kind of like alluding to that trade-off I talked about earlier, where if you replicate your inputs, you've got more stuff to put into the vectors, but you sort of save some of this data movement. Okay, so of course there's evaluation numbers. So I'm just reporting a subset of the benchmarks here, but we ran a bunch of benchmarks. We ran them with like 3 different replication strategies with both inputs unreplicated, one of them replicated, and both of them replicated. There's also this sort thing where we like sort a list of 3 elements. And that we also ran with this like ungrouped policy, which basically just means that none of the elements were required to be packed into vectors, and they were all fully replicated. The key things that I want to highlight here is we on like the more vectorizable things like the matrix multiply and the dot product, we see like some significant speedups, like between 2 and 3x over scalar. And crucially, like replicating is almost always faster. Like with the matrix multiplies, you can see like the yellow bars are like way higher than the blue ones. For the dot product, it doesn't matter because there's no like repeated, like nothing gets used more than once in a dot product computation. And even for the sort, like replicating and ungrouping gives us a little bit more vectorizability. And this is sort of what you'd expect, because in this actually, I think this kind of highlights like an important distinction between vectorizing in FHE and vectorizing in a sort of more traditional setting, because in a traditional setting, you don't always want to replicate your inputs because this like data movement stuff is relatively cheap, right? You can just like scatter gather, or you can like select things and like move them around. But you only have like a very small fixed number of lanes. And so like using up extra lanes is pretty bad. But in the FHE world, it's like the exact opposite trade-off. You've got like tens of thousands of lanes available to you. And so using up extra vector lanes is like almost nothing. But saving that extra rotate is very important, because like the only way to do this is with these like very expensive rotations. And so it becomes it just becomes like a very different trade-off that you have to worry about. Okay, so in conclusion, Coyote is a compiler that vectorizes arithmetic circuits and takes into account an FHE specific cost model. It works by trying to minimize the data movement overhead that you get by vectorizing by working at the level of like subcircuits, like contracting these edges instead of working at the level of individual instructions. And we see that it like finds optimal data layouts that encourage more efficient rotation patterns. And of course, we see that the vectorized code is faster. I've got a QR code here to the paper. We also have an artifact available, like all the code is up on GitHub. So the paper has a lot of other cool stuff, like the rest of the benchmarks that I didn't show here. We did a few case studies on like looking at different data layouts and stuff, and then it's got some more sample code. So please check that out. And yeah, that's it. I guess we can move to questions.
Can do a quick question over here.
Mhm.
I was wondering, so you said like what you were saying about the replication, oftentimes improving things makes a lot of sense. Although I was wondering, presumably it matters what you're replicating. If what you're replicating has a bunch of multiplications and whatnot, right? Wouldn't that actually make things more expensive? And so related to that, I was wondering if you thought about adding something to the DSL to summarize this kind of information to the users to help them make these decisions on what they should replicate, kind of like some statistics. If you replicate this, you know, this is the estimated cost without actually having to test it.
So the in terms of like replication, if the thing that you're replicating has a bunch of extra multiplies, that's true, but it often doesn't matter because all of those extra multiplies can get vectorized into the same thing anyways, right? So if it's the same thing, but I'm just computing it twice in two different lanes, I can vectorize those computations perfectly. So I don't end up actually doing any extra work, right? It's one vector multiply whether there's one lane active or two lanes active. But in terms of like providing some feedback to the users in the DSL about this kind of thing, we haven't looked at that yet, but that would definitely be like an interesting thing to like try to do. I'm not super sure how easy it would be to like estimate the schedule costs before doing any of the like expensive search, but I think we could probably get some kind of like reasonable estimates on that.
Okay, thanks. Questions?
So do you have a picture of how replication affects memory usage?
Memory usage. Oh yeah, so like if you look back here, the nice thing is like replication doesn't really, right? Because when I've sort of this is another sort of like abstraction that I haven't drawn here, but if you look at like T1 here, there's 4 elements in it, but T1 here has like 4 elements, but like more of them are filled in. These vectors are actually I don't know, like a few thousand lanes wide, and we're just using the first few lanes of these. So the ciphertext vector is going to be the same size no matter how many things you put in, because the rest of it's just going to be padded out with zeros. So as long as your replication isn't putting you over the like 8,192 lane limit, it doesn't show up in the actual like size of the ciphertexts or anything like that. Which is why I was sort of saying, like in the world of FHE, everything is so huge and so slow and so bad anyways, that like replication really doesn't matter, or there's not like really any overhead to it.
So related to that, then, why did you choose to expose it then, if you should kind of pretty much always replicate? Why should the user tell you when to not do it?
The time you might not want to replicate is if you're trying to like compile 2 functions separately, but you want to end up composing them. So if like the matrix that I'm getting is if like A is not just an input, but it's the output of some other computation, then replicating A might cause its layout to be really weird, and then I'd have to do some more work to get the output of that other computation to sort of fit into whatever layout it chooses for the replicated A. This is actually something that we're working on right now. So right now the DSL doesn't really think about this compositionality, and it just kind of like vectorizes one function, and then you're sort of responsible for like figuring out how to make these things line up. And so in that case, like you might not want to replicate it. But yeah, that's a problem that we're sort of actively trying to solve right now, is like how do you compile things separately but still be able to reason about like compositionality and stuff.
So would it make sense to integrate the replication as another kind of knob in your optimization problem, or does it not make sense because the overwhelming majority of the time you want to replicate, at least within a particular procedure.
Yeah, so I think you mean like having the compiler automatically figure out when to replicate?
Yeah, I figure you already have these sort of like put the R's in the right place in the lane and figure out how to quotient the circuit. Another knob might be, do I replicate, do I not replicate per lane, I guess, or something like that, per R for each like lane, right? You could make that part of your optimization problem, but I'm wondering if like it increases the search space by a ton, and most of the time a heuristic does pretty well, and so you might not want to do that. I'm just wondering if you've what the trade-off is there.
Yeah, so the search space is already kind of big. I'm not sure how much searching for replications would increase it. But I do think that the heuristic of just always replicate is pretty good as long as you have this, like, as long as you're able to compose two replicated kernels together properly, which is sort of the reason why right now we just expose it to the programmer, because we don't know if they're going to like compose things later, or like we don't know how they want to use the vectorized code here. And so it becomes kind of like it becomes a question of intent more than efficiency. But yeah, I think in general, like once you've got this composition thing working, you pretty much just always want to replicate things.
And you mentioned that the user is responsible for sort of tying different functions together. Does that mean that they might be responsible for like inserting a rotate between like in between the composition of two functions or something like that? And if so, like how does that affect in particular the optimization problem that gets applied to an individual procedure, right? So that procedure might say, oh, for this circuit, in a world where this is the only circuit running, the optimal sort of layout for these inputs into a particular lane is this, but of course, based on the other functions that might be producing values for that input, that may actually not be the optimal layout because you might need to rotate in between. Is that right? Or am I making something, am I wrong?
So that's essentially correct. So there's like there's two ways that you can do this if you have like a bunch of like subcircuits that sort of compose together. One of them is you stitch everything into one giant circuit and just optimize across that whole circuit, right? Search space is huge, but if you're willing to wait for however long it takes, then it'll come up with an answer. The other thing, it's like right now this requires a little bit of manual effort, but you can if you like, you can specify the particular input layout that you want for one of the inputs. So like here for like A, it's chosen like 0, 1, 1, 0, 0, 0, 1, 1, right? But you can specify a particular thing that you want. And so if you've got like one circuit feeding into the inputs of another one, you can vectorize the first one, look at its output layout, and then require that to be the input layout of the other one. And then it'll kind of like optimize relative to those fixed boundaries. And so of course there might be a better schedule that like knows about the fact that like these inputs are coming like from this other place and optimizes across. But that's always what you give up when you like compile separately, right?
But it's a good idea, right? Because you get the advantage of being able to sort of manually apply this kind of greedy algorithm. But presumably, since the optimization problems are over, individual are sort of intra-procedure, intra-function. They can be performed. You can perform, n of them. Again, like we could go another layer out. You could parallelize your your optimization, right? And so yeah, that's interesting. All right. Well, do we have any other questions before we?
So you mentioned you can do XYZ if you're willing to wait a long time. How long is a long time?
So for these smaller ones, like a 2x2 matrix multiply takes like a couple seconds to compile. I think the biggest benchmarks we ran were like point cloud distances for like a set of like 5 or 6 points. Those took on the order of probably like 9 to 10 minutes. So it's definitely not super fast, but it's probably comparable to like like a synthesis problem, right? Like it's not going to be any kind of like real-time compilation, but for like a really big circuit, I don't know, maybe like a couple hours and it'll like find something reasonable. There's also the search procedure has like timeouts on it. So like simulated annealing, you just run for a certain number of rounds, and if you're willing to increase that, then you get better results, but it'll stop after a certain amount of time and just give you the best schedule it's found no matter what. So that's another sort of like knob that you can play around with. But yeah, for our benchmarks, we're looking on the order of like a few minutes probably for some of the bigger ones.
Yeah, related to that, have you looked at, I imagine when you do the search and you're kind of limited on resources, you may want to kind of, what you were saying, get the best I found so far, but I imagine you might want to schedule your searches in a different way. Have you looked at like do you just control how long you optimize each node? Or is there some kind of a breadth first searching or like prioritizing in what direction to search things? Is that
so the search over the graph uses like a beam search, right? Where it opens a certain number of nodes in the graph and like optimizes all of those and then puts them into a priority queue and then grabs like the top few from the priority queue and opens their neighbors and so on. So it's sort of like a best first order of searching.
Okay, so then you can kind of almost stop at any time and you have the best I found so far, kind of.
Yeah.
That's kind of nice.
Hi, hello.
Hi.
I was going to ask a question about sort of how the compiler handles, say, bootstrapping. I think you mentioned bootstrapping in the paper concerning like FHEs and how sometimes noise can, adding too much noise, you'd lose like the ability to decrypt your the ciphertext. So is it, does your compiler in any way, like if the depth of the multiplication gets like too deep, is it possible to lose the ability to recover the actual ciphertext? Is that something that's, I don't know if that's a valid question?
Yeah. So the compiler itself, like the DSL doesn't the DSL and the compiler don't really think about stuff like bootstrapping. The particular FHE implementation we link against does some kind of automatic bootstrapping like every time you multiply. There is like, you could, for example, like look at a circuit and try to figure out based on like the multiplicative depth whether you'll need bootstrapping for your particular set of encryption parameters or whatever, and then maybe try to like do some optimizations to like minimize the multiplicative depth. That's not something we do here, but that is certainly something that you could like stick on as the compilation phase before vectorization. But yeah, most of the details of the FHE implementation and like bootstrapping and stuff like that just happens in the FHE backend. So we just compile down to like this like basic instruction set that has like multiplies, additions, and rotates.
All right, thank you so much.
Okay, is that it?
I think so. Richard, you've got an echo going on.